Welcome to the Biogas module. This module aims at understanding the importance of biogas, the process that produces it, and its applications, as well as the theoretical and technical aspects needed to obtain a broad knowledge of this renewable energy. Here we shall frame this within the energy and environmental context in the region of Latin America and the Caribbean. Biogas as a renewable energy source has aroused great interest in recent years and is perhaps one of the technologies that is easiest to implement, especially in rural areas. Its potential development, not only considering the production of biogas, but also its environmental connotations and obtaining a biofertilizer, make its applicability and dissemination highly attractive in sectors that produce a lot of waste with high organic matter contents. Energy consumption on the Earth is not uniform, and there are significant differences between the different zones of the planet. Activities which in many cases are assumed to be routine and easy, such as cooking, lighting, or access to electricity, can for many people on the planet become a daily challenge. This challenge includes the availability of the fuel needed. Systems based on the production and use of biogas can solve many of these problems and help to improve the quality and the standard of living of people in many zones, and specifically in the region of Latin America and the Caribbean. We must also bear in mind that there are increasing energy needs and therefore increased power consumption. Meeting these growing needs of the various countries and protecting the environment require new technologies, new partnerships, and new ways of operating. Millions of tons of organic waste are generated across the world, as in the case of municipal waste, manure, agro-industry waste, and sewage sludge. Some of them are especially important in Latin America and the Caribbean, which are markedly livestock and agro-industry oriented regions. So we see that much waste is generated, with a high content of organic matter. The treatment of these wastes is accompanied by unavoidable costs, because there are regulations to be complied with. However, if the waste is treated considering criteria of minimizing energy consumption, energy production, nutrient use, and a reduction of greenhouse gas emissions, anaerobic treatment becomes very attractive. The high concentration of organic matter in waste makes them highly suitable for use as feedstock in anaerobic processes for biogas production. Of course, the waste must be suitably managed, and there are well-known problems associated with this when wastes are not treated properly. There is also growing awareness that environmental precautions are essential for the future of our planet and continued economic development. We now have technology that is able to debug waste and at the same time produce energy. This is known as anaerobic digestion. Environmental aspects and the need for renewable energy have led this technology to be of huge interest in both developed and developing countries, since it offers both possibilities and solutions to global issues, such as safe, controlled waste management, energy production, and other collateral benefits. Anaerobic digestion is a biological process in which a group of specific bacteria, anaerobic bacteria, transform organic matter into biogas and a nutrient-rich product known as a digestate, or biol, in some countries of Latin America and the Caribbean. There are different strategies for managing this digestate, and the appropriateness of one or the other will be governed by the characteristics of the environment, the objectives, and the scale of treatment. Some authors have attributed the first scientific reference to biogas in 1630 to Jan Baptista von Helmont, who stated that a flammable gas could be obtained from the decomposition of organic matter. The scientific interest for energy purposes dates from 1776, when Alessandro Volta identified the relationship between organic matter decomposition in an anaerobic environment and the generation of a combustible gas. Over the years, Many researchers, among which are some of the most famous scientists in the world, have advanced our knowledge of the process, but it was only since the mid-20th century that more progress has been made, and today many of the reactions involved are now well known. Throughout history, there have been many events related to the evolution of research into biogas. In 1930, for example, with the discovery of anaerobic bacteria, there came the academic and scientific recognition of anaerobic digestion. However, subsequently, this interest began to wane owing to the increasing consumption of fossil fuels. It was from the oil crisis of 1973 when interest resurfaced. Research and development programs were promoted and industrial plants were built. There are many reasons that justify biomethanation, among them energy production, scarce and strategically very important resources, and the great potential of biodegradable organic waste in the region of Latin America and the Caribbean. As I have mentioned, this is a markedly agro-industrial and livestock-oriented region. All these activities generate millions of tons of waste that could be used to provide energy and at the same time meet the requirements of sustainability and environmental friendliness. Another fact to note is that biogas is a renewable source of energy and thus provides greater supply security. Its use also reduces emissions, thus contributing to the reduction of greenhouse gas emissions by avoiding methane. Finally, of course, it is a source of employment. Biogas also provides greater energy and economic independence. The rising costs and limited availability of renewable energy sources, combined with the difficulty of distribution in rural areas, make the application of this technology particularly appropriate in these communities. Moreover, nationwide, it can help to reduce the import of other energy sources. Another fact to consider is the versatility of biogas, since it can be used in many energy applications. At family level, in rural areas of developing countries, it is used mainly in kitchens and lamps. On a large scale, its main applications are direct combustion for heat production and in cogeneration engines producing electricity and heat. Other areas that are gaining increasing importance are its use as fuel in motor vehicles and its injection into the natural gas network. Finally, we should note that organic waste has a natural microbiological activity due to its composition. This implies that there are natural processes of decomposition and that an inadequate control of its management allows gas, including greenhouse gases such as methane, to be emitted into the atmosphere. The application of anaerobic digestion is also effective for the appropriate reduction of greenhouse gas emissions. Biogas has two origins. It can be produced in anaerobic digesters or naturally in sanitary landfills for municipal solid waste. Biogas generation in both digesters and in landfills is a process of interest in the energy field. In both situations, there is a significant environmental improvement to be gained, since the extraction of biogas from landfills reduces methane emissions and the anaerobic digestion of the waste reduces pollution. This slide shows the schematics of the process that takes place in an anaerobic digestion plant. The organic waste enters a digester, and different microorganisms are able to transform it into a gas, composed mainly of methane and carbon dioxide, and digestate, which can be used as an organic amendment because it improves soil quality. Inside the digester, the organic matter is transformed by the action of different families of microorganisms. Biochemical and microbiological studies indicate that the anaerobic degradation process can be divided into 4 phases: hydrolysis, acidogenesis, acetogenesis, and methanogenesis. When the waste contains sulfates, small amounts of hydrogen sulfide can also be produced. Due to its biological origin, All the gas, methane, CO2, etc., produced in the process is known as biogas. Biogas is constituted mainly of methane, between 55 and 65%, carbon dioxide, 30 to 40%, and other gases in small concentrations, lower than 5%. Biogas is a source of energy equivalent to other conventional sources. The slide shows the equivalence of 1 cubic meter of biogas containing 65% methane with respect to traditional energy sources such as fuel alcohol, gasoline, natural gas, electricity, and wood and coal. In the case of electricity, we would of course have to factor in motor performance. The United Nations organization considers biogas as a very important renewable energy, especially in the region of Latin America and the Caribbean. It is claimed that biogas can boost the agricultural activities of small producers and reduce greenhouse gas emissions in these and other regions of the planet. As we have seen previously, the anaerobic digestion process is produced by different groups of bacteria. It is desirable to maintain these microorganisms under optimum conditions in order to obtain higher efficiency in the process. Organic wastes have different biogas yields. The slide shows biogas production from different wastes. Depending on the loading frequency, there can be batch, continuous, or semi-continuous digesters. In this case, the digester is fed discontinuously but steadily. Depending on the degree of development, digester technology can be divided into two groups. First, we have basic technologies. These refer to family digesters whose primary objective is to provide energy. But there are also advanced technologies, which are oriented to the agricultural and agro-industrial sectors at upper middle level. In this case, the objective is to provide energy and resolve pollution problems. Family-scale digesters are widespread in countries like China and India. The digesters most employed are, respectively, the fixed dome and the floating drum. However, the complexity of their construction and the relatively high cost compared to Taiwanese models have limited their implementation in other countries. The tubular plastic digester, a simple and inexpensive construction, allows further expansion of this technology. These digesters operate in semi-continuous mode. A fixed amount of manure is mixed with a fixed amount of water, and the mixture is introduced into the digester once daily. The global aim in the development of these digesters is to reduce costs and to increase the life of these facilities in order to reach the largest number of users of this technology. Tubular polyethylene digesters are the type most frequently used in the Andean zone. They are made of plastic, are easy to build, and are economical. Experiments carried out show that a digester of 8 meters long can treat the waste of 55 pigs and produce up to 6 cubic meters of biogas per day. In the Andean region, the majority of energy is consumed in the home, and consumption is based on the use of traditional biomass, such as wood and dung, which involve serious health problems, especially in women, and also environmental problems. A program has been carried out in this area that aims to promote the use of family digesters as an alternative energy source to the use of traditional biomass. After China and India, Latin America, with 10,000 digesters, is the region with the most small-scale, low-cost digesters. In recent years, important progress has been made in understanding the process, both as regards the microbiology involved as well as the parameters that regulate degradation. This has led to significant improvements in its efficiency. The main objective of advanced technology digesters is to achieve maximum performance by treating waste efficiently and economically. Currently, many different technologies are available, and the choice of one or another depends mainly on the characteristics of the waste to be treated. These digesters are classified in 3 groups according to how the microorganisms are located in a digester. Microorganisms can be present in suspended growth, attached growth, on a carrier support, or they can be divided into two groups of bacteria, using two digesters, to favor the specific conditions of each group individually. Complete mixed digesters were the first to be developed. They are technically simple, with long hydraulic retention times of 15 to 30 days. They are mainly used for wastes with high concentrations of suspended solids, such as livestock waste and sewage sludge. Plug flow digesters are simple, with a long hydraulic retention time of 20 to 30 days. This type of digester is mainly used for livestock waste treatment. Anaerobic contact digesters have shorter hydraulic retention times than the two previous digester types, between 2 and 6 days. They are mainly used for the treatment of agro-industrial wastewater, such as effluents from papermaking and sugar factories, among others. In UASB digesters, the hydraulic retention time is 1 to 2 days. Greater volumetric loading rates can be achieved than with anaerobic contact digesters. They are also used for treating agro-industrial wastewater, such as from sugar factories, brewing, coffee, etc. Although very high volumetric loading rates cannot be achieved with them, anaerobic filter digesters are very stable. The hydraulic retention time is similar to UASB digesters, and they are also used for the treatment of agro-industrial wastewater. Fixed film digesters have the same characteristics as anaerobic filter digesters. The main difference is that the inert support is placed in a set, that is non-random, packing configuration. Usually the direction of flow is downwards. The hydraulic retention time in expanded bed digesters is very low, just a few hours. These digesters are used for wastewater with low concentration of suspended solids. The unexpanded bed occupies about 10% of the digester volume. This type of digester is called an expanded bed digester when the resulting expansion of the bed is between 15 and 30%. Fluidized bed digesters are similar to expanded bed digesters, the main difference lying in the degree of expansion of the bed. In this case, it is higher than 30% and may reach 100%. To achieve this expansion, it is usually necessary to recirculate part of the influent. These digesters are used with wastewater containing low concentrations of suspended solids. As we have seen previously, the anaerobic digestion process takes place in several stages. Each involves different kinds of microorganisms with different metabolic properties. The latest advanced anaerobic digestion technologies seek to separate the phases and optimize them individually. Two-phase digesters consist of two digesters, and each one carries out one part of the fermentation process. In both China and in Germany, recently built advanced technology anaerobic digestion plants have undergone significant growth. The official data provided by the Fachverband Biogas, FVP, the original name of the German Biogas Association, confirm the important development in recent years of this technology in Germany. The FVP notes that in 2011 more than 1,310 new plants came into operation. This is equivalent to 650 megawatts. The trend has not slowed, and it is estimated that by the end of this year there could be a total of 7,895 facilities generating 3,312 megawatts. In Latin America and the Caribbean, anaerobic digestion plants are now being used for important projects, not only from an environmental perspective, but also from the point of view of energy. Such is the case of the anaerobic digestion plant that Brugal has set up in San Pedro de Macorís, in the Dominican Republic, to treat the stillage generated in the distillery. The stillage is treated by two anaerobic filter digesters with a capacity of 1.93 million gallons. 75% of the volume of the digesters is occupied by a PVC plastic support. The digester is designed to produce 24,000 cubic feet per hour of biogas with an average feed of 28 cubic meters per hour. The biogas produced is consumed in one of the two existing boilers, achieving a considerable saving of fuel. Plant data show that anaerobic digestion is an established technology that can yield environmental and economic benefits through biogas production. The project known as Biogas is an unusual strategic project including a collection of interrelated scientific and technological activities with a common aim. This is to develop sustainable systems for producing and using biogas in agro-industrial environments, as well as demonstrating its viability and promoting it in Spain. In total, 15 research and development centers and 16 Spanish companies and organizations have participated in the Biogas project. The project is backed by the Ministry of Science and Innovation through its aid program for unique and strategic projects. As discussed above, biogas is also produced in solid waste landfills. In a sanitary landfill, as they are known, municipal waste is discharged on the ground and spread out, forming thin layers. Then the waste is compacted to reduce its volume and covered with suitable materials to minimize the risk of environmental pollution and to promote the biological transformation of fermentable materials. When a landfill has completed its waste capacity, it must be sealed. It is in these conditions that the biological degradation of the waste organic matter and biogas generations occur. To prevent leaching in landfills from affecting the soil, groundwater and surface water, the base lining has impermeable barriers and adequate drainage layers. Also, once the landfill has been closed, it is then sealed with different layers in order to avoid the emission of gases to the atmosphere and the entrance of water into the installation. The biogas production process in a sanitary landfill occurs slowly and takes place in 5 phases. Methane formation starts in the 3rd phase and reaches its maximum in the 4th phase, approximately 2 years after the discharge of the waste. The extraction of biogas is considered necessary from the environmental point of view to avoid the emission of greenhouse gases such as methane into the atmosphere, and also from the energy point of view, since it can offer a significant energy potential. An installation designed for the extraction and utilization of landfill biogas consists mainly of wells, pipes, valves, control and monitoring equipment, pumps, and flame exhausts. The slide shows a Spanish landfill gas plant. Here we see a diagram with the main elements responsible for the capture and recovery of landfill gas in a large sanitary landfill. During the past 30 years, several models have been advanced to estimate biogas production. Of these, the most widely used in the Latin American and Caribbean region is the LandGEM from the United States Environmental Protection Agency. This has made versions adapted to the characteristics of some countries in this region, such as Ecuador, Colombia, Mexico, and Central America. The model is based on a first-order equation which estimates the amount of biogas and the constituent gases produced in the landfill. The figure shows one of the graphs obtained with the model. The main function of landfill bioreactors is to accelerate the degradation of organic matter. Biogas will be produced at a higher rate than in traditional landfills. Settlement will also be greater. The percentage of methane will increase, and the greenhouse effect and the presence of toxic gases will be reduced. This implies higher profitability, less environmental damage, and a reduction of costs in post-sealing maintenance. The moisture content is the most important factor because it promotes rapid degradation. Bioreactor technology is based on maintaining optimum moisture levels, approximately between 35 and 65% relative humidity, by the addition of liquids, usually a leachate. The addition of leachate or liquids is accomplished with pipes, which may be positioned either vertically or horizontally. As we saw above, one consequence is that the bioreactor produces more biogas in a shorter period of time than conventional landfills. This last figure shows the results obtained after several years of research conducted in 2 pilot cells in Yolo County Central Landfill in the United States, one a control and the other a bioreactor. As you can see, there is a much higher methane production in the bioreactor cell than in the control cell. This is corroborated in the attached images, where a higher settling rate in the bioreactor cell can be observed. The good results achieved in the pilot testing have led to a demonstration plant.